Hi, Andreas.
Hi.
Can you talk to us a little bit about the most vital parameters, machine parameters that are involved in soil compaction and how those parameters affect the compaction process?
Yes, of course. There are several factors affecting the compaction performance actually, and the first and single most important one is the so-called static linear load. And the static linear load is simply the axle load for the drum module of the machine divided by the width of the drum.
Okay, so since we're talking about load, is there some way that we could use a scale to measure that?
Yes, it's possible. Imagine that you put a scale beneath the drum of the roller, reading the value indicated by the scale and dividing this value by the width of the drum gives you the static linear load.
Okay, very good.
It's very important actually to choose a machine with a sufficient static linear load for the specific job to be carried out. Otherwise, the compaction requirements might be difficult or even impossible to fulfill.
Okay, so you've explained to us the static linear load now. It is the single most vital parameter for the compaction performance. What are some other parameters that are slightly less important?
Well, then we have the drum vibration amplitude. And the drum vibration amplitude is defined as half the distance the drum moves during one compaction cycle. And the magnitude of the amplitude mainly affects the compaction depth.
Okay, so if the amplitude is affecting the depth, I would assume that that somehow relates to the layer thickness that you could compact.
Yeah, you're absolutely right. A machine with a high amplitude can compact thicker lifts compared to a similar machine with lower amplitude actually. The operator normally has the possibility to switch between a high amplitude setting and the low amplitude setting.
Okay, so if a high amplitude setting is an option and it's more efficient, we can do thicker lifts, thicker layers. Why would the operator want to choose a lower amplitude?
Well, the low amplitude is used for compaction of thinner lifts, but also to be able to continue the compaction work if so-called bouncing occurs at the high amplitude setting.
Okay. So now that we've talked about static linear load, we've talked about amplitude, I think the next one that comes to mind and is obvious is the rolling speed. How does rolling speed affect things?
Yeah, the rolling speed of course also affects the result, and a low rolling speed is beneficial for the compaction depth. However, it reduces the capacity of the machine. So, based on testing and analysis, the operator should strive for a rolling speed of approximately 1 meter per second, that's 3 to 4 kilometers an hour, to achieve a good compromise between compaction depth and capacity.
Okay, so critical point, 3 to 4 kilometers an hour is the ideal rolling speed, duly noted. Are there any more parameters that you'd like to discuss?
Well, I would like to point out that the number of passes over the same area also affects the compaction result. However, the number of passes required to fulfill the compaction requirements is dependent on the setting of the parameters previously mentioned, but also on the compaction frequency. It's clear though that by choosing a machine with a sufficient static linear load and by tuning your parameters such as amplitude, rolling speed and compaction frequency, the number of passes can be reduced. And this in turn saves you both time and money. For example, if you could fulfill your compaction requirements within 6 passes instead of 8 by tuning your parameters correctly, you will end up with approximately 25% lower running costs.
Okay, quite a significant change in cost. You mentioned a little bit about frequency that we didn't talk about before when we talked about static linear load, amplitude, speed, and number of passes. Can you talk a little bit more about frequency?
Yes, of course. The compaction frequency is actually a measure of how many times per second the drum hits the ground. And the compaction frequency is normally preset by the machine manufacturer to a fixed value. For soil applications, this frequency is normally in the range between 28 to 33 Hertz. However, from our latest research, we have found that the compaction frequency significantly affects the compaction result if it is tuned to the dynamic characteristics of the soil.
Okay, so up until this point I was following, but now you mentioned dynamic characteristics of the soil. Can you please elaborate on that a little bit?
Yes, the dynamic characteristics mainly relates to the stiffness of the soil. We want to achieve a high soil stiffness because that is the same as a high load-bearing capacity, and that is what we want to achieve with our compaction. Now, if we can tune the vibration frequency to the dynamic characteristics of the soil, several benefits may be achieved, such as reduced fuel consumption, reduced number of passes, less wear on your machine, and so on. On many modern rollers, the operator has the possibility to manually adjust the vibration frequency within a narrow range. However, to manually identify the dynamic characteristics of the soil and adjust the frequency accordingly is an impossible task.
Okay, so I hear what you're saying, and you're indicating that it's impossible. However, I feel that there's a but.
Yes, to make the impossible possible, Dynapac's engineers have developed the revolutionary Seismic system, which will ensure that the machine always runs at optimum compaction frequency.
It's really impressive. Thank you very much for taking the time today to talk to us about this and share a little bit more about the Seismic system from Dynapac. It's really going to bring us into a new era in compaction. Thank you.
Thank you very much.